All right, well, I would like to start, like everybody else, by thanking the organizers, by which I mean Renzo, for inviting us all to Erice for such a lovely meeting. It's my first time in Sicily, and I'm sure I speak for everybody that's still here when I say that it's been really excellent. So thank you very much. We've all had a fantastic time, but I know there's a lot of effort goes into organizing these things. And we're all very grateful to you for doing it. So today, I would like to tell you about my recent work on topological chirality. This is joint work with former student of mine, Joseph Pollard, who's now a postdoc up in Durham. Okay, so I should start by saying a few words about chirality in general, and then also the particular flavor of it that I'll try to talk about. So here is a photograph of Lord Kelvin that I took for Randy whenever I was postdoc with him. This is the statue to him in the Botanical Garden in Belfast. And he introduced a kind of generic definition for chirality, which we continue to use and find useful to this day, that things are chiral if you take their mirror image and the object itself and its mirror image are distinct. And here I illustrate this with an example that we've seen a number of times throughout the workshop, which is this knotted vortex line constructed in William Irvine's lab about 10 years ago. And I think it's an appropriate example for a couple of reasons. First of all, this is an example that actually is chiral. It's chiral in the sense of the curve that we're looking at, but also it captures the sort of chirality that I want to talk about today, which is that this is not just some curve, it's not the actual vortex filament itself. This is a full three-dimensional fluid flow, and we've constructed some kind of interesting knotted and also chiral structure in a three-dimensional field. And that's the sort of chirality that I will talk about today. Okay, well, the specific system that I will tell you about, or that I have in mind when I'm thinking about these problems, are liquid crystalline systems. And I'll show you a few pictures of them, much in the spirit of what Randy did in his talk, where I show you some selection of experimental images in an effort to try and impress on you that our experimental colleagues can do really remarkable things with these materials. And one of the advantages of this system over a number of others is that there are beautiful images to work with, and also that standard optical microscopy techniques are enough to give you really very detailed structural information about the materials. But in general, I should say that I want to talk more in slightly general terms about topological chirality in continuous fields. So you can think of it as some continuous vector field, and that it's specifically a liquid crystal that I have in my mind hopefully should not be terribly important. And if at any stage you're unsure of anything, please just interrupt and ask me to explain. Okay, so there's a variety of different things on this slide. The particular ones that I will talk about today are the ones that are in the top right corner. These things are called Cholesterics, and somehow they have a character of chirality associated to them. So let me try to give you an idea of what that means in this context. But before that, I want to say a few more words about what liquid crystals are. I put on the slide this presentation that Randy went through in his talk, where you look at them under cross polarizers, you see that they have interesting optical properties. This is roughly speaking why we make displays out of them. And so a good characterization of what a liquid crystal is it's a material that does something interesting optically. And so I can capture that at macroscopic scales, the scales that are represented by this picture, by picking out of the dielectric tensor its anisotropic part. So that's one way of thinking about liquid crystals. And another is in terms of whatever the alignment of the individual constituent molecules happens to be. And so I throw up an example of this type where you can see what the local alignment is, not because this is an electron micrograph, but because the individual molecules are rather large, and then you can see them under standard optical microscopy. So this is the suspension of microtubules. And the feature that you see here is that locally they like to align in some kind of direction. If you go to a different part in the material, then they align in some different direction. And then they also have this feature that there are places where the alignment is poorly defined, and that if you walk around those points, you discover that the alignment rotates by some multiple of 2 pi, and that multiple is a half integer, positive or negative. So this is an example -1/2, an example +1/2. And Randy already said the important part about this, which is that just from looking at these images, you can see that these liquid crystal materials have this so-called nematic symmetry, that they're described really by line elements rather than little vectors. And that can be important for some characterizations, but as I said already, I'm not going to emphasize on this. So it's enough just to think I have a little vector field. They have defects in them. The defects characterize much of their properties. So I'll summarize the sort of early things that were done in thinking about their defects. There's the story that Randy described in his talk, which is that you look at these so-called Sriram textures and you count the brushes that come together at various points, and you calculate the windings around those. And this process was formalized, at least in the physics literature, in the 1970s with applications of homotopy groups. So we tend to think that you take measurements on some circle going around points in the sample. So you're measuring on some circle, you're taking values which are orientations of the molecules at the various points you sample. Here, if you're sort of in the plane of the screen, then line elements in the plane of the screen is RP1. You look at its fundamental group, it's the half integers. And the same story goes through also for three-dimensional materials, with the distinction being that when you're in a three-dimensional material, there are two types of defects. You either take this picture and extend it along a one-dimensional curve, and you get some kind of line defect. Then you do exactly the same story. You calculate pi1 of RP2, and you discover this is the group Z mod 2. So there is a single up to homotopy, this particular way of measuring the defects in the system. It tells you that there's one of them up to continuous deformation. But also there can be isolated singular points. So genuine isolated points in three-dimensional material. These ones you interrogate by measuring what's happening on the surface of a sphere that encloses them. And so you pick them up in homotopy language with pi2 of RP2, which is the integers. And this integer is something that Randy explained how to calculate, and also the same thing, but in higher dimensions, was in Paul Sutcliffe's talk, amongst other things. Okay, well, there is a little bit more to the characterization of defects in these materials than just the homotopy story that was developed in the 1970s that I tried to summarize on the previous slide. And here are two examples of it that are roughly speaking from about 10 or 15 years ago that come from adding little small micron-sized particles into the material. These are particles with certain boundary conditions, so they provide, let's say, Dirichlet boundary conditions for the vector field on its surface that are radially away from the surface of this particle. And that looks effectively to the material like some kind of little defect, and it compensates for it by a defect of its own in the bulk surrounding material. And it can do it in a variety of ways. It can do it as a little genuine point, or it can take this point, blow it up into a little circle, move the circle from the right of the picture onto the equator of this colloid and make this ring-like configuration. So one of the things that's interesting is that not only do you have lines and points, but you can interconvert between them. And that interconversion between them is reflecting some higher order structure that there is in the homotopy group description of defects in these materials. And then something that occupied me for quite some time, but which I won't talk about today, is that if you have the right experimentalist, it turns out that you can take these curves and manipulate them and tie them into all sorts of different knots. And then ask questions about what are the properties of knots in this sort of system? What's the classification of liquid crystal textures with different types of knots? Okay, well, I'm going to talk about things that are chiral. So I should add a few words about what is a chiral liquid crystal or what is a chiral vector field. And the basic example that I'm going to make use of is the one that I've tried to sketch here. So there are, I think, 3 ways that you can think about this, and I encourage people to find their favorite. There is a sketch made with Mathematica on the left-hand side, and maybe some people will find this a useful way of thinking about what cholesterics are. There is an explicit formula for a vector field in the middle of the board, and then there are some actual experimental images. So feel free to choose whichever one of them you find easiest to get some idea of what these chiral materials are. The idea in terms of this picture on the left is that I have alignment of the molecules at any particular location. So let's say, as indicated, that everything points horizontally. And at any given height, everything is all pointing in the same direction. And then I go in some perpendicular direction, say the vertical one, and it rotates at a uniform rate. And that rotation can be either right-handed or left-handed. And that's exactly the notion that we have of some type of chirality in the material. I'm going to try and work exclusively with things that are right-handed, or as much as possible with things that want to be right-handed. That's just some convention. Okay, well, I want to take a brief detour to show you how this fits into a general geometric description of liquid crystals, but I'll say again of the geometry of vector fields. The main difference with what I'm thinking about here, as opposed to the completely general case, is that what I have in mind is that I'm keeping track of the orientation of things. So I have a direction, but not the magnitude. So I'm thinking about unit magnitude vector fields, if you like. And I want to try and say something about the geometric properties that they contain and how you can decompose those into pieces and study the topology. So an idea that we have been using for a while, which turns out to be insightful, is that if you're given some directions of some vector field at every point in space, then you are also given at the same time the little two-dimensional plane which is perpendicular to that. Right, so if you have the direction, then also say, for instance, the vertical direction, then you also immediately have the plane that's perpendicular to it, say the horizontal plane. They're completely equivalent. You're free to choose whichever one you think is the most useful. And what at least I have found is that some problems are easier from one perspective and some problems are easier from the other. So what really I have taken away from this is it's useful to know both of the representations. And I give here 2 canonical pictures of what this correspondence looks like. You can look either at the little cylinders, that's the vector field, or at the little two-dimensional planes, and they're conveying exactly the same information. Okay, so what do you do to extract geometric properties from this unit vector field? Well, we look at its gradients, and we look at its gradients split into pieces according to its symmetry principle. Symmetry principle is that if I give you an orientation, some line element at this point, then there's an action of the rotation group that fixes that direction. So there's a little local rotations about whatever that direction is, which fixes that particular orientation. And that's a subgroup of the rotation group that's isomorphic to SO2. And what I do is I take the gradients of the director field and I break it up into pieces that transform independently with respect to that action. So at the crudest level, that separates out into derivatives, a differentiate in the direction which is parallel to my little locally defined orientation. So I have parallel derivatives, or I differentiate in one of these perpendicular directions. So that's the first decomposition. This one gets the name of band. And then the other one, which is, this is a direction that's perpendicular. So it's an X or a Y of a unit vector along Z. When I differentiate unit vectors along Z, I get back a vector which is again an X and Y. So I have something which is in the XY plane for the gradient part, and after I've differentiated the vector, it's again in the XY plane. That's a little 2x2 matrix, and I break it apart into its pieces. It breaks apart into 3 pieces. Those pieces are the identity transformation on the orthogonal plane, the complex structure on the orthogonal plane, and then a piece which we came up with a stupid name for. We refer to it as the deviatoric part of the orthogonal gradients. And if people know of a nice or snappy name or something that's like from about 1850, where people have named this, I would be delighted to hear. So far, I haven't found it, but it seems like a kind of basic thing. So that's the structural part. In terms of what they represent, I have these little cartoons. And then I've tried to associate the geometric properties that you get from these. So this one is telling you about the curvature of the integral curves of the director field. This part is telling you something about mean curvature in the vector field. The one with twist is the one that I'll focus on for today. And then this part, which is anisotropic, it picks out preferred directions in the perpendicular space. And those are directions of principal curvature, or also some high directions of principal twisting. So I'll say a few general things kind of briefly about this. The first one is that you can, of course, construct the standard free energy for liquid crystals out of this. We have decomposition into independent pieces. You form scalar quantities, stick material-dependent coefficients in front of them, and write them down as some kind of free energy. This is loosely speaking exactly what Frank was doing in his foundational paper. We just write it in slightly more modernized notation. And for what I'm going to talk about today, the thing that is different from standard liquid crystals is that I allow myself one additional parameter in the energy. That's this number. This is the amount of some chiral molecule that some helpful chemist has synthesized for you and told you you add so much of this molecule to your existing material and you'll make a nice right-handed material. Okay, let me run very quickly through a couple of things that you can extract from this decomposition. So the first that I'll look at is this band. As I said on the previous slide, what is this? This is the rate at which the direction is changing as you go along the integral curves of the vector field. Each integral curve is some curve in space. I'm calculating the rate of change of its direction, so that's just the curvature of that integral curve. That curvature, as we all know, it's oriented perpendicular to the curve itself, so it lies in these orthogonal planes. It's a vector field that lies in these orthogonal planes. So that's the first property that it has. There's some technical jargon here, which I will try to avoid using later on, but if it crops up, I put it on this slide. We call these Legendrian vector fields. And how do you study vector fields? The basic study of vector fields is you look for where they vanish, and you study windings of the vector field around them, and you apply a Poincaré-Hopf theorem to those. And the only difference here is that in this particular case, because these are vectors in, say, the XY plane, their zeros are codimension 2. So they form a family of one-dimensional curves in the material. Okay, here's an example, some complicated figure that I tortured one of my graduate students into producing for me a few years back, illustrating, for instance, in blue, the integral curves of some interesting structure, and in green, the zeros of band. The same is true also for this funny piece on the right-hand side. Again, it turns out to be effectively a two-dimensional vector, and you study it through its zeros. And again, they're a family of one-dimensional curves. And I said already this part that because it's a little 2x2 matrix, it has eigendirections, and those are directions of sort of principal curvature in the material. So it's also interesting to look at those. Right. What I really want to talk about is the twist part. And for the twist part, there are sort of a couple of stories that I will tell. The first one will depend less on this. The second one maybe a little bit more. What we have found beneficial in the past few years in trying to bring new ideas into the characterization of these materials is the connection with contact topology and contact structures. So I have some definition on the board, which either makes sense to you if you've seen it before, or maybe not, and I'll try not to explain too much if you haven't. From our perspective as a theoretical physicist, roughly speaking, what it means is that if I shift perspective from the vector field to the planes that are perpendicular, then what I was calling a cholesteric is what the mathematicians were calling contact structures. And it's loosely speaking what this says. And the part that I'm going to focus on and try to extract some insights from is this generic observation that liquid crystals have defects in them. So there are singularities in my vector field or singularities in my family of planes, and I want to study their properties. And in particular, I'm going to be interested in the basic question of if I have some kind of defect in the material, then how does that defect make itself compatible with the requirement that there should be an intrinsic handedness in the vector field? And I'll give you two examples of this. So the first example is for point defects. This is a tremendously complicated slide if you've never seen it before. So let me try and simplify it as follows. There are a collection of experimental images where people really concretely make realizations of these chiral materials with defects in them. And we have to try and understand what it is that they're looking at and come up with some description for it. So I'll try and run through what I understand about it more in pictures and conceptually than giving you the fine details of everything that's going on. The things that we'll be interested in that I'll try and convey to you is that there's not just a single thing here, right? Often, for instance, if we have some energy or something like this, you look for the structure that minimizes the energy. You hope it's a unique structure, and there'd be one picture on the pleiage. That would somehow be an ideal situation. And here, that's not the case. There are many pictures and many more than the ones that I am able to squeeze into this slide. Then also there's a separation between defects that like to sit in the center of this droplet and those that like to sit right up close to the surface. We'd like to understand what the difference between those is. And then also this basic question that I have, how do these manage to maintain a right-handed structure around them? Okay, and I want to condense the understanding that we developed of this into a particular example and just talk through that example and ask you to trust me that this particular example captures all of the features that are going on. So the example can be motivated as follows. I take the energy that the vector field is trying to minimize, and I look at it in a regime where this chiral part, the part that tells me that there's a handedness, dominates over everything else. So let's forget about the first term, forget about the third term, and worry only about the second one, and ask myself, how do I minimize the energy? And the answer is I minimize the energy if I can take this object, n dot curl n, and set it equal to the constant value minus q0. And I have a trick for doing this The trick for doing this is that I forget about the fact that I want to work with a unit vector field and give myself an arbitrary vector field, which has some magnitude associated to it. And I look for vector fields with variable magnitude that are curl eigenfields, so that have curl M is equal to this CM number times itself. And then if I take that particular solution and normalize it, it gives me a unit vector that satisfies this condition. Okay, so concretely, that's what I'm going to do. And I'm interested in defects in the material. And now that I've given myself a magnitude to my vector M, defects in that vector field are going to be zeros. So I'm really interested in zeros of curl eigenfields. And the strategy for studying them is the typical one that physicists do. We're going to write down a little Taylor series and look at it and see what we can pull out of it. So here's the Taylor series for a zero. The constant part of the vector is 0 because I want it to vanish. Then it has a linear piece, then a quadratic piece, then higher order pieces that I hope I never have to think about. And I write down schematically the structure of this curl eigenfield equation. So I take my vector field, I calculate its curl and see where everything goes to and ask it to match up. Okay, so to get something that works, there are a number of properties. The first one is that if I want the linear part to vanish, then the curl of something locally, if a vector locally its curl vanishes, then locally that vector is the gradient of a function. So the first part is that the structure of all of these zeros, all of these defects, is that they're given locally by the gradient of some function. And then you have a higher order piece, which guarantees that it has the right handedness. Let me summarize 3 things about this construction, which turn out to be significant for understanding what's going on. The first one is that generically point defects are not chiral. That's because for it to be chiral, I had to have that the curl of this linear part vanished identically. So that's the, if you like, the X, the Y, and the Z component of this 0 are all 0. That's 3 conditions. So these things are at least codimension 3. The second one is that the structure is given by locally by the gradient of a function. And so the classification is not just the classification of zeros in a vector field, but rather of critical points in a function. So they should be classified by singularity theory, which is a little bit unusual. And the last one is that the function itself is a harmonic function. And that's because if I take the divergence of this thing, I have the divergence of M, but I find M up here, M is equal to the curl of something, so its divergence vanishes. Okay, so these are also interesting in that they're harmonic functions. It tells you immediately you have the maximum principle about harmonic functions. It tells me that the critical points are always saddles. You never get maxima or minima. Okay, so how to connect this to the observations? The first connection is that I said generically these defects are not chiral. The generic ones are not compatible with a well-defined handedness. That means the material doesn't like them. If the material doesn't like them, it will try and get rid of them. And the best that it can do is push them to the surface. So the distinction between the defects that sit in the interior in these experiments and those that sit on the surface is that the ones that sit on the surface are generic zeros, which are not chiral, and the ones that sit in the interior are special. Okay. And the picture that I have here, the color coding is that if you have the correct handedness, you're blue. If you have the wrong handedness, you're red. So that was one part. Then the second part was this connection with singularity theory. This I refer to as the catastrophe of Cholesterics. So there's a classification of all of these critical points in functions due to a number of people. The version of it that I list here is Arnold's celebrated ADE classification of the elementary catastrophes. Here are beautiful examples from optics. Mark, were these taken by John Nye or Michael? Okay, so beautiful examples in optics taken from John Nye. And you can ask yourself which of the singularities that appear in the big long table actually are observed in the experimental system. And so far we've identified the following ones. So there are the kind of elementary generic or Morse type singularities of Morse index 1 and 2, omitting the maxima and the minima by the maximum principle because these are harmonic functions. And then of the higher order singularities, you find this nice one, D4 minus, which has this structure, matches the experiment very nicely. And then you jump immediately to one which is much more complicated, which is one of these unimodal singularities with multiplicity something like 10 or 11, which is way up in the list, and they call T44. But again, the model that you get from using this is remarkably similar to what they see in the experiments. You can do more with the singularity theory because it not only tells you about the classification of critical points of functions, it also tells you how to break them apart into different pieces. These are the unfoldings of the catastrophes. And so you can look for those also in the experimental data. I show you one here, which is an unfolding of the D4 minus singularity, and then also two separate examples that they find in the experiments, which turn out to be unfoldings of this higher order T444 singularity. Okay, so the last part I want to say a few words about is this last point that the function is harmonic, that is to say that things have to look like saddles, or put differently, that there are no maxima or minima. So what happens here is that, say that, put the statement up again, the critical point has to be a saddle. What that means is that it can't be a local maximum or minimum. That means a radial structure to the director field is somehow bad. And it turns out it's bad in a fundamental way, and a fundamental way which has a topological origin associated to it. So let me try and say something about that, and also how it crops up in the experiment. So here I show an example of an experimental realization of a droplet with a single defect at the center, which sits in the interior and so should have some chiral structure associated to it. But it's realized in an experimental system where it's in a finite volume, so in some spherical droplet, and there are boundary conditions on the surface, and the boundary conditions are that on the surface of the droplet, the vector field wants to be normal to it at every point. So even though the structure is not radial around the singular point itself, you still force it to be radial by boundary conditions at the surface of the droplet. And that turns out to be bad. So that turns out to enforce some region where the handedness in the material is distinct, or has the wrong sign. Let me put it this way: if I want the material to be right-handed throughout the droplet as much as possible, then there necessarily is some region somewhere in the material where the handedness is left-handed instead. Okay, so let me say a few words about where this comes from. Maybe I'll go back here and say, we discovered this is some result of Ellie Ashberg and Thurston in their study of what are called confoliations. It's their Rabe stability theorem. I'll try to give you some idea of what these words mean, at least as I understand them. So the way that Thurston proves it is he uses this geometric description of what is meant by twist. The idea is to compare and contrast the difference between things that have a twist, a handedness in them, and things which absolutely do not. The things that absolutely do not are foliations or smectics, which is what Randy was talking about. And in that case, the vector field is the normal to a surface. So I draw a little simple example of it. And What one can do if it's the normal to a surface everywhere is you can take a little small loop on that surface and calculate this line integral. It's 0 by construction because n is the normal to the surface and the contour lies in the surface. So n dot ds is 0 everywhere. You apply Stokes's theorem and it's telling you that for this condition, this twist has to vanish. So when it's not 0, when you have a chiral material, then something else has to happen. And the pictorial way that you can think about it is that you tilt or you twist the director field away from the surface normal everywhere. And then as I go around this curve, I follow a trajectory which isn't in the surface, but rather which is everywhere perpendicular to this vector field. And if I do that construction, then when I go around once, I don't come back to where I started. I end up by some amount or down by some amount. And the part that's important here is that if the material is right-handed, then as shown, you end up higher than you started. And if it's left-handed, you would end up lower than where you started. Okay, well, this interpretation of twist allows you to at least outline the proof of this theorem in a number of steps. You take a spherical surface that the vector field is normal to, you break it into two disks with the equator as a common boundary, and you calculate this shift either up or down around the boundary from the perspective of both of the disks. And the point is that they share the same boundary, but with opposite orientation. So that if for one of them, the displacement is in the positive direction, then the other one necessarily has to have a displacement in the negative direction. So it's not possible to put right-handed twist on both hemispheres of this little sphere. Okay, so that's where this frustration is coming from. And here, just a reminder that it tells you that in a neighborhood either of anything which is locally radial, either because there's a singular point or because I have boundary conditions in some finite domain, then there must necessarily be some region which has the wrong handedness. Well, here's a strategy for coming up with other examples of this. This is an example in a cylindrical capillary. So I put this in a cylindrical tube. It's not in a sphere anymore. And the fact that it's not in a sphere means that there's no hard, fast topological reason for why there has to be any regions of reversed handedness. But we can construct them or we can introduce them in the following way. So what happens in this system is that I have the vector field confined to some cylindrical region with normal anchoring boundary conditions. So everything is sort of radial at the outer surface. And when it gets towards the axis of the cylinder, it has to decide what to do. Is it going to stay in the radial direction and have some singularity along the axis, or is it going to try and avoid that? And if it wants to avoid it, it can do it in two ways. It can either choose to rotate so as to escape in the upwards direction along the axis of the cylinder, or it can choose to do it in the downwards direction. And the game that we play with this system is to ask it to make different choices in different parts of the cylinder. So for instance, here in the little cartoon, I have some region where it escapes down, connected to some region where it escapes up, and at the interface between the two, there will be some structural defect in the material. Well, these have been studied for some time, and one of the things that's interesting about them is that they have this non-abelian character, which is to say that if you order them down and then up, this is not the same as the ordering up and then down. You see the distinction between them by the structure of the defects that are associated to them at the transitions. And the main feature that arises here is that at the interface between up and down, the local structure of the singularity that you introduce into the material is that it points radially away from wherever the defect point is. So in this way, you force in part of the material that has this locally radial structure. And that should be topological. So here's a couple of simulations of the configuration just to illustrate this. If the strength of the chirality in the material is relatively mild, then the structure that you get is a combination of a defect, which locally has this radial structure and has some regions around it with the correct handedness, but also some regions with the wrong handedness. And then also some little tubular object going around the boundary of the cylindrical capillary. And if you crank up the strength of the chirality, you can get rid of the regions of reversed handedness around the defects in the interior. But the existence of this region was topologically protected by this theorem of Eliashberg and Thurston. And so it has to persist in at least some form. Okay, well, that's the story I wanted to tell you about point defects in chiral vector fields. For the last few minutes, I'll say a few words more briefly about line defects. So here, to start with, again, I show a selection of images from experiments and also from numerical simulations of singular lines in chiral materials. These ones are harder to understand what's going on. You have to do some kind of more complicated or more sophisticated three-dimensional visualization. So I don't really want to point to specific features in this slide, just to convey the idea that there are a number of experimental realizations, again, with a variety of different structures that they see. So there's not a single thing. We have to try and explain why there should be many things. And I should also say that, of course, there's been theoretical ideas on this going back a long time, going back to, I think, 1969 and then 1970 from the French group, which provides a description of the different things that you see and a formalism for thinking about what they look like structurally and how you should name them, which is a little bit analogous to the sort of homotopy classification of defects that I mentioned briefly at the start. And what we're looking to do is to try and bring some new ideas, some slightly more geometric ideas, to look at this classification from a more modern perspective. So that's what I want to try and explain. And what we've come up with so far in this direction is to give a classification of the local structure of singular lines in chiral vector fields based on concepts that are coming from contact topology. So concretely, what I'm going to do is the following. I want to characterize the structures that are compatible with being right-handed, not everywhere in space, but just in some little neighborhood of this singular line. So the blue curve is supposed to be some singular line. I look at some immediate neighborhood of it and characterize what are the local structures that are compatible with being right-handed everywhere. And the three concepts which go into characterizing this are a basic dichotomy that the contact people use, which is the distinction between things that are tight and over-twisted. Then some tool that they use, which is have the names of convex surfaces and dividing curves, and then some topological invariant, which guarantees you that the things that you're looking at are different. And I'll try and show pictorially what these things mean. So here, this is the notion of tight and over-twisted. There's a definition, which you can either read or ignore. To describe it pictorially, I showed you a number of times these pictures giving basic illustrations of plane fields and the connection between thinking about a vector field and thinking about a field of little two-dimensional planes. And it turns out that the two pictures that I show are genuinely different from each other in a topological sense, and they illustrate this dichotomy between things that are so-called over-twisted and things that are so-called tight. Now, for somebody like myself, who comes more from a physics perspective, it's fine to have nice definitions, but I want to try and connect it to things that people see in experiments. So far, the best that I've come up with in trying to convert this into pictures that my experimental colleagues take are two examples. On the one hand, I showed you previously that there's this interesting interplay between point and line defects in liquid crystals. You can convert points into lines and vice versa. So it turns out that any of the lines that shrink to a non-trivial point, they're all over twisted. Okay, if it shrinks to a trivial point, then it's tight. Otherwise, it's over twisted. And then also there are these skyrmion configurations. And the skyrmion configurations are, loosely speaking, exactly this technical definition. So they're also all over twisted. The significance of this dichotomy is that there is this basic theorem which tells you that the over twisted case has already been solved and the tight case is hard. And so our effort in thinking about these things is to classify the tight structures. And then I said the tool that we're going to use is goes with the names of convex surfaces and dividing curves. It took me forever to get some idea of what a convex surface is, so I hope I don't butcher it too much by taking a physicist approach to this and saying that one of the most important characterizations of the technical definition that they came up with was that it was generic. So morally speaking, you pick any surface that you like, and it will have this convexity property. In other words, what we're doing here is that instead of studying the vector field at all points in space, you study it just on some surface. And if you're unlucky, you'll pick a bad surface, but generically, you'll pick a good one. And then what do you do with it? Well, you extract from it the set of points where the director field is tangent to the surface. So here on the left, I show a couple of examples of this construction. I have the vector field, and then I have it plotted by some color function telling you its orientation in the horizontal plane. And on the right-hand side, I replace this representation of the vector field with the one that's up here. So I draw the surface and a bunch of lines on them. And the result is that you can characterize topological properties just by thinking about this picture with the lines. So that's what we're going to do. And the result here is that if you're looking at this construction on the surface of a torus, so here I want to apply it to a defect loop. I have this blue line, it closes into some loop. I get a surface by taking a tubular neighborhood and looking at the boundary of that. So that's a torus. And I draw this curve. Here I draw a part of this curve. And in other examples below, I also draw some parts of the curve. And the result here is that the classification of the different red lines, the different patterns of red lines that I can possibly draw, was made a little over 20 years ago by Honda. It's classified into how many components so how many separate parts to the curve are there, and then also what the slope is. So is it mostly vertical, is it mostly horizontal, or somewhere in between? And for each of the possibilities, you can write down an explicit representative for some director field, which corresponds to a line with a particular slope and particular number of components. Here's some list of what those look like. Okay, well, that brings me to the end of what I wanted to say. So let me wrap up. And usually, I am not so fond of lengthy conclusions and summaries. I have hard cuts. but I wanted to include this quote of Charles Frank, so I put it on the board for you, that I have liked very much ever since I started as a PhD student, and I think reflects the sort of things that we have been doing at this meeting, that we have been trying to talk about topological things and find useful things to do with them. And with that, I would like to stop and answer any questions.